Okay, so we're going to start going over this. Look at your structure here. So someone tell me one bond that you're seeing that's going to have polarity. Go ahead. Okay, good. So your oxygen-hydrogen bonds are definitely polar. If you look at your difference between your electronegativity, you're seeing it's much higher than 0.4, right? If you subtract this, we're looking at 1.24. So anywhere in here where there's an OH, you're going to see polarity. So you can get that noted in here, circled, whatever you want to do. But I want to show you, too, how we reference these. So, like, for example, there's an OH on the screen that I just circled. When we use a dipole moment, you're showing where those electrons are closer to, okay? You're going to see me draw these. I'm not going to have you required to draw them. I just want to expose you to this, especially if you decide to take AP Chem. This is something that's talked about extensively. So when we draw these, we want to say, okay, where are the electrons closer to? So the one that has the higher electronegativity is going to pull the electrons closer to itself. It's obviously our oxygen, right? Much higher electronegativity than our hydrogen. So what you would do to show that you'll see me draw here, again, I'm not requiring that you do this. This is called a dipole moment, where you essentially have that this end is the more positive one. It looks like a plus sign. And then this end is showing the electrons are actually shifting in this bond closer to the oxygen. Okay? That's just because the oxygen is much higher in electronegativity. So when you see me draw those, I'm just showing you which direction those electrons are actually being pulled in. So as you think about these covalent bonds, I almost want you to envision the electron's dead center being shared. Except if it's polar, instead of being dead center, think of it like tug of war. They're actually way closer to the oxygen than the hydrogen, okay? That makes the oxygen like the hydrogen itself like a partial positive charge, meaning like they're almost getting pulled away from it, but it's not a complete charge. If it was a complete charge, we had to have that difference greater than 1.7, which we're not quite there, okay? So it's kind of like that in between. All right, good. So there's one other types of bonds that's in here. Now you could circle all of the OHs, okay? There's one other type of bond that you're seeing in the structure that is also polar. Ethan. Okay, good. Carbon and oxygen. So if you go to your carbon and oxygen, so any of them, so like for example here, just so I pick one that's not right next to it. Any of your carbon-oxygen bonds are also polar. We look at the difference between those. Oxygen is definitely still the more electronegative one, so you could draw that same idea that the electrons are actually way closer here to the oxygen than they are to the carbon. So instead of being dead center, they're closer to the oxygen. Okay? Now, carbon-carbon is obviously nonpolar. You would take 2.55 minus 2.55 is 0, so there's no polarity between the same elements. There's also no polarity between C and H's. If you subtract, we're at 0.35, which is less than 0.4, so it's not polar either. They're shared dead center. With sucrose, the reason that it can dissolve so well in water, even though it's covalent, when we look at it, it can dissolve because you're seeing all these OH bonds, which are also in water, right? So we've got that similarity between the types of bonds that are also polar. That's what allows sugar to interact with water and dissolve. Something ionic, like sodium chloride, dissolves so well because there's these charges. But something that's polar covalent, like this is, with a lot of polar bonds, can also dissolve. Okay? Questions on this? Okay. So let's actually look at, okay, so if I gave you a structure, how would you tell me if it's polar or not? Okay, so we're going to do some examples. So we're going to do 5 here, and then you'll take it from there. So CH4, right? Now, here's the true process. You would draw your Lewis dot structure, you would determine the VSEPR and go from there. But if we're doing just a quick polarity check, you can take some shortcuts here. If it's CH4, the bonds are between which 2 elements? C and H. Is there any polarity between C and H with your electronegativity? No. So you can just answer pretty quickly that there would be no polar structure as a whole because there's no polar bonds. Okay, remember what you should have written. You need it to be asymmetric with polar bonds. We don't have polar bonds, so there's no way this structure could be polar. Okay, so you could really quickly be like, hang on, that's not even a polar structure. Let me not go down the route of drawing Lewis dot structure and doing the VSEPR. Okay, so not polar. That's what you would say. Okay, now we'll look at what actually happens when it is polar, but that one's a no. CO2 is the next one, okay? So I'm thinking, what are my bonds between? My bonds are between carbon and oxygen. I do those quick check of subtracting there. I'm definitely in the range of polar, okay? So we should draw that out real quick. Remember that we already did that on the last page, so I'm just going to draw it. If you flip back, you would see this structure, okay? Now, you could go through the process and start from the beginning, but for it to be a polar structure, it has to have polar bonds and be asymmetric. So we have polar bonds. However, hopefully you'd argue it's pretty symmetric. Like if I cut it right down the center, it looks the same on either side. So because I have two really negative things on the outside, but they balance each other out, it's symmetric. It's not polar as a whole, okay? So you would say this is also a not polar or non-polar compound, okay? Now let's do NH3. Again, all of these ones that we're doing, we already drew on the last page, so I'm just going to redraw them. Okay, you can always check back on 35. You'll see we drew these structures. So if we look at what the actual structure looks like in VSEPR, okay, it looks like this. And again, if you flip back a page, you'll see that we have this. It's a 3-1 configuration. Okay. So do we have polar bonds as our first question? Between the N and H, yes. Okay, if you subtract those. So now we got to check, is there an area where there's more positives versus negatives, or is it symmetric? Okay, so I'm hoping you're seeing with me this does not feel very symmetric. Along the bottom, we have these three, this is like a tripod. So along the bottom, we have these three H's. Along the top, I've got this lone pair of electrons. Electrons quite literally are negatively charged. So if I show you this real quick with the structure, it looks like this, okay? So along the bottom, I've got these really low electronegativity hydrogens that are kind of positive because they're getting the electrons pulled away from it. They're getting it pulled to nitrogen, all three of them. And then I also have a negative area on the top. So it's almost like all my electrons are getting pulled up. So I've got this area that has this high negative area at the top, positive area at the bottom. Okay, so since it's not symmetric, that can tell you that this is a polar-based compound. We have this area where it feels like there's almost more negative here, more positive otherwise. So you would say, yes, this is polar, okay? Now the true answer, if we were to actually diagram this, like I kind of keep showing you here, is all of your electrons are getting pulled up. So it's like the top half of the compound is more negative, the bottom is more positive. Okay, let's look at PCl6. If you remember this one from yesterday, we did this one to start. Oh my goodness. If we do this one again, just so you can see it, we're looking at this octahedral configuration like we looked at yesterday and even into today. If you look at that as a whole, PCl are the bonds between P and Cl polar from the difference on the board. Between P and Cl. Yes, they are. Thank you. I was getting concerned. So if you look at this, right, we've got the P, we've got a Cl at the top, we got a Cl at the bottom. We've got two of them that are kind of coming out at you. We just drew this one to start off today. So we've got a lot of polar bonds. All those P-Cl bonds are polar. Next question is this a symmetric structure? Okay. I would say yes, and hopefully you agree. There's Cl's around the entire thing. You literally have them coming out as you're going back, up and below. So there's no area we can be like, hold on, there's a lot of electrons there. That would cause it to be polar. So you would say this one is non-polar because it's symmetric, okay? And the last one we're going to look at real quick is water. We looked at water structure a decent amount. Again, we started off today too with that. So we've got this area up top. That's 3D. And I think we already know this even from bio. Water is a polar structure. And if I'm looking at Y, up above, there's a lot of electrons. So that's a negatively charged area. Below, the hydrogens are getting electrons pulled away because these are polar bonds between them. So for sure, this is a polar structure. Okay? If you wanted to look at it again, it's like the electrons, again, are getting pulled up. So area on the top, more negative. Area on the bottom, more positive. Okay? All right, so here's what I would like you to do. If you can grab your practice packet, we're going to work on a bunch of problems here.